Okay, YouTube, in this video we're going to introduce the concept of graphing rational functions, and specifically just starting off with simple rational functions and then branching outward. And so let's go ahead and start by talking about what a rational function is. We define a rational function as being any function of this form here. So what we see essentially is, we want to point this out here, some function of x, where that's equal to the top expression is a function of x over some bottom expression is some function of x, but we have a ratio. And so this is where this idea of a rational function comes from, is because we say that really a rational function is just a ratio of two functions, where specifically p of x and q of x are polynomials. So just kind of a refresher, remember that polynomials are these expressions that we often list that have real coefficients, okay? And the exponents here on our x variables are all positive, or I'd say non-negative integers. And so something like this would be a polynomial. We could say, something like 4 minus x to the fifth. Maybe that's not in standard form, but that's a polynomial. If we were to do this right here and say that this is some function, this would be an example of a rational function, just an example. Anyways, moving forward from here, we would say that one important stipulation here is that we do not allow q of x to be 0. And so we'd say that q of x cannot be 0, but the reason why is because that would cause it to be undefined. So we avoid this at all costs. We say that the inverse variation function, as a matter of fact, this f of x equals a over x, or you may have seen k over x is a rational function. We could say that that's an example of a rational function as well, because we were looking at functions that when we express them, some k over x, then our constant of variation there, maybe it was like 4 over x or something like this. You could certainly see that 4, even though it has no variables here, it'd be some 0-degree polynomial. And then this x to the first here is just a polynomial. So this certainly would qualify as a rational function. So when we talk about simple rational functions, what we're going to do is we're going to start with this graph right here, and we're going to allow our a value to just be specifically 1. It's always good to kind of look at a parent function here. And so what we're going to see is, this is really important, is that this is going to be the breakdown for our parent function of the graph of y equals 1 over x. And so what I want to do here is, I've kind of used up this space unwisely. What I want to do is I want to make a table of values. And in terms of this table of values, I just want to talk about the behavior of our graph as x changes here. So it looks like on our window that we see right here, x goes from like -5 to 5. Let's do this. Let's go -4 to 4. And so as we do this, these are really kind of easy to evaluate. We'll get an idea or a sense of how our function values behave if f of x is equal to 1 over x. So in each possible instance, what we're doing is we're taking 1 and we're dividing by the input, or the x value. So in this case, we would get -1/4, okay, -1/4. Here I'll squeeze in a -1 over 3. Here we get -1 over 2. Here we get -1 over 1, which is -1. And then when you plug in 0, I'm actually going to write this out. We get 1 over 0, which, just to be clear, is undefined. So 1 over 1 is 1, 1 over 2 is a half, we have 1 over 3 is a third, and 1 over 4 is a fourth. And so we could see, at least to a certain extent here, there is some level of symmetry that occurs amongst these values. And so when we look at the graph here, let's go ahead and take a look at some of these points. You'll notice that when x equals 0, our graph, this is this set of two blue branches here, is what we'll call them here in a second, but it does not even proceed over this x value of 0. So one very important thing that we want to point out right off the bat is that the graph of a rational function will not exist if the denominator equals 0. And for this graph right here, that occurs specifically when x equals 0. And so we would say that x equals 0 is a vertical asymptote. And certainly you can see that this is listed on the picture here. But what we want to acknowledge is this. This is because the f of x is undefined. And so what we're going to see regularly is that we'll have asymptotes, vertical asymptotes, wherever our graph is undefined, wherever we divide by 0. Okay. And so looking at this here, we could also see that as x is, say, getting bigger and bigger, our y values are getting smaller and smaller and smaller and smaller. If you went up to 100, you'd be at a height of 1/100th. So as our graph goes to the right here, you can see that at 1, okay, let's go ahead and put this point on the graph here. The point 1, is kind of a key point here. We always kind of memorize as being on our graph here. And let's go ahead and highlight this one as well. -1, -1. These 2 points are on this parent function consistently if the a value is 1. So we would say that going from 1, 1, we would say, you notice that at 2, we go to a height of a half. At 3, we go to a height of a third. At 4, we go to a height of a fourth. As we continue to go to the right, what you're going to see is that these values are going to continue to get smaller and smaller, but they never reach 0. So maybe we make a note here, never progress to 0. This is a truth. But what this is going to imply is that we have a horizontal asymptote on our graph at y equals 0. So very clearly, we can see that these graphs of rational functions, or at least this parent function that we're going to memorize here, is this set of branches that we'll call them branches here in a second, I promise, but has a couple of asymptotes. One at x equals 0 where it's undefined, and one at y equals 0 where it'll never reach, but it'll always get close to on either end of its graph, okay? And so reading through this, we say that the graph of the parent function, okay, is what we call a hyperbola. So the shape of this blue graph here is a hyperbola. And we say that a hyperbola, in this case, consists of two symmetrical parts called branches. So with these blue sections of the graph here, we say that this is a branch of the graph, and this is the other branch of the graph, and it has multiple branches, but this is all one function, okay? We say that the domain and range are all non-zero real numbers. So when we talk about the domain, we're going to list this explicitly here. We're going to write all real x values except for what? Well, all real x values except, and I won't write except, we'll write this. We'll say colon, and what this will stand for is such that, or it is the case that. We say all real x values such that x is not allowed to be 0. And this is how we'll write the domain. We'll say all x values but that. In terms of range, we can see that our graph here hits all y values below this y equals 0 and all y values above it, but it doesn't hit y equals 0. So we'll say all real y values, okay, such that y is not allowed to be equal to 0. So with this graph here, we say that any function, and this is the important part we're going to take away from this here, because we're going to go graph our own here in just a moment, but it says any function of the form g of x, where g of x is a over x, and we say that this a value is not allowed to be 0, but we say that it has the same asymptotes, same domain, and same range as this function right here that we refer to as the parent function, okay? The parent function, just 1 over x. And so using this base knowledge here, this base knowledge of this 1 over x graph, I'm going to keep this in my back pocket. What I want to go do is graph g of x here, which is 4 over x, and I want to compare it to the graph of 1 over x. So let's go ahead and do this. We're going to say f of x, okay, is our parent function, is 1 over x. We're going to put it on this grid, and then we'll put g of x over here, which is 4 over x. And so one thing I'm going to encourage us to do is, at least in a small part here, let's go ahead and identify some x values that we're going to plug into this function. So I would say that a good battery of x values, in this case, -3, -2, -1, 0, 1, 2, and 3. And so keep in mind that 0 here is going to cause the parent function to be undefined, and this will be true for both of our graphs. As a matter of fact, g of x will say 0 is undefined when we plug a 0 in for our x value here. So what we're going to see is that we have a vertical asymptote at x equals 0 because we can't have our function defined there. And as we plug in our points, we say 1 over 1 is 1, 1 over 2 is 1/2, 1 over 3 is 1/3. Here's this symmetry again. We get negative 1 over 1. Let me just write -1. We say -1 over 2 and -1 over 3. What I want you to see is that as we graph these, we say 1, 1, 2 comma half, 3 comma third. As we go to the left side here, we say -1, -1, which is right here, -2 comma -1/2, -3 comma -1/3. You can see this symmetry here, and you get this intuitive sense where the branches would go. So we can clearly see that our horizontal asymptote does certainly lie here at y equals 0. And this is going to be true of any function of this a over x form. So when we sketch this in, we say here are two branches. We'll just go ahead and throw those in there. Should have put this in an orange color here. Let's do that. And we'll come in from this way. We say this is the behavior of our graphs. We just get really close to the asymptotes here. But mostly the graph is just interesting here in the middle. On the ends, it's not very interesting. So looking at 4 over x, I'm going to do the same thing here. I'm going to say -3, -2, -1, 1, 2, 3. It's actually really important for me, for you to see how these output values will change with 4 over x here. So we say, what if we plug in 1? Well, we get 4 over 1. We would get 4. How about 4 over 2? We would get 2. How about 4 over 3? Well, we get 4/3, which is 1 and 1/3 is what I'm going to write here. And as we do the negatives, keep in mind we get this level of symmetry here, -1 and 1/3, because we're just taking a positive 4 divided by the negative of these positive values that we did before. So throwing this together, pretty simple. We would say, well, what do I know about the parent function? We have an asymptote at y equals 0. And we say we have a vertical asymptote at x equals 0. And plugging in the rest of these points, we'll see how this affects the graph here. We could say that at 1, we were at a height of 4. We were at a height of 4. 1, 4. We say 2, comma 2. And then we say 3, comma 1, and just a little more than that. Here's our branch on the right here. I'll put this in orange. So we see this branch on the right we're going to get some symmetry here on the left side. Let's put these in. We say -1, -4. So that'd be down 4 here. -2, -2, and -3, comma, -1 and 1/3. We would say here's this branch right here. Okay. So in terms of how this compares to our original graph, you could see that all of these points here that were originally, I suppose, at 1, 1 and -1, -1, those are the 2 points we tend to identify all of the time. They've been vertically stretched, and it looks like by a factor of 4. And so we're going to see that going forward here that our A value has to deal with some vertical stretching of our graph. I would say, more generally speaking, if we take a look at this, I just want to see this transformation here. As we open up, say, Desmos, and we put in a graph here, we'll say f of x, which is our parent function, equals 1 over x. And we go down, we say g of x is a over x. We're going to be able to see as we put in a slider for a here. I want you to see on the graph. Let me zoom out just a little bit here. You can see this point 1, 1. Here's this point 1, 1 and -1, -1 a little bit more clearly. As we change our a value here, you can see that a value really is going to directly correspond, most in particular, with that point 1, 1. We're going to say now where it was at a height of 1 before, now it's going to be at a height of 5 because we've quintupled all of our y values here in order to get to this point right here. If I can get it right on 5, that would make my day. Boom. Okay, so 5. Anyways, you can see that this a value causes stretch, and foreshadowing a little bit here, you can see that if a is negative, we're also going to get some x-axis reflection going on as well as stretch. So that's how you graph a very, very simple rational function of the form a over x. As we go into the next video, we'll take a look at some transformations. Cheers.